Welcome to this explainer. Okay, today we are diving headfirst into a question that honestly keeps AI researchers awake at night. How do we actually know for sure if an AI is truly thinking, or if it's just, regurgitating data? Well, we're looking at a pretty groundbreaking new paper today. It's Archive 2067.05436, and it actually proposes a rigorous mathematical way to prove if an artificial intelligence has achieved genuine intelligence. So let's just dig right in.
So let's tackle the big one. Are large language models truly intelligent, or are they literally just highly sophisticated pattern matchers? I mean, this is basically the core existential crisis of modern AI scaling right now. Up until this point, we've kind of just relied on vibes, basic benchmarks, and perplexity scores, but we haven't had a rock-solid mathematical way to tell the difference between a model that simply memorized the internet through continuous interpolation and a model that has actually autonomously discovered a brand new causal law.
All right, here's our roadmap for today. 1. The AI intelligence crisis. 2. Failing under OD pressure. 3. The geometric breaking point. 4. Measuring genuine discovery. 5. Filtering out hallucinations. And finally, 6. Next steps for developers.
Section 1. The AI intelligence crisis.
Classically, we've always treated learning systems as these flat optimization landscapes, what we call classical flat Euclidean statistics. In this old-school view, the model basically treats any new variance it sees simply as noise that it just needs to absorb. Because of that, it mathematically cannot differentiate between just interpolating old data and discovering something causally new. Enter statistically meaningful geometry, or SMG. This totally shifts away from those flat assumptions and instead models these systems as curved, complex shapes, specifically infinite-dimensional non-parametric Orlicz fiber bundles. It's a mouthful, I know, but think of these bundles like hidden layers of geometric fabric that can actually bend and warp. The absolute crucial point here is that geometry now dictates behavior, which gives us a structural way to track exactly when a model crosses over from simple pattern matching to true, genuine discovery.
Section 2. Failing under OOD pressure.
So the researchers pinpoint a fascinating structural failure mode that happens when a model encounters persistent out-of-distribution or OOD stimuli. Imagine you're feeding the AI data that's driven by a completely unfamiliar causal rule, something it has literally never seen in its training set. In those old, flat statistical spaces, the algorithm just blindly tries to absorb this new rule as if it were random noise. But under sustained, continuous pressure from this unfamiliar data, continuous optimization simply fails. The flat mathematical assumptions just completely break down under the sheer weight of an unmodeled reality. Let's actually walk through how this builds up. Think of it kind of like the hero's journey of a machine learning model under immense stress. Step 1, the model tries to handle the unfamiliar data, but the visible horizontal base manifold totally rejects it. So that variance leaks into the hidden vertical fiber space. Step 2, this leak generates a massive accumulation of what the researchers call active achiasal tension. Step 3, guided by the nonlinear curvature of the manifold, this tension inevitably strikes a hard geometric limit, a conjugate focal boundary mathematically defined as T crit equals pi squared over k max. And then step 4, hitting this boundary triggers a localized volumetric collapse and a catastrophic matrix singularity. The hidden layers are literally buckling under the math.
Section 3. The geometric breaking point.
Now, when you hear the phrase catastrophic matrix singularity, where the inverse metric tensor blows up to infinity, your first instinct as a developer is probably to completely panic and restart the training run, right? But this beautifully illustrates the core thesis of this whole framework. This volumetric collapse is absolutely not a bug. It's not your standard training failure or a divergent gradient. Instead, it acts as a strict non-equilibrium trigger. The model has basically hit a brick wall where its current understanding of the universe is completely inadequate, and it is entirely forced to adapt. And that forced adaptation leads us to this incredibly profound definition, the gauge symmetry break, or GSB. Because the system can no longer handle that hidden tension, it's literally forced to purge it from its unobservable gauge redundancies. And the result? The spontaneous crystallization of a completely new, mathematically independent horizontal coordinate axis. It's like the model suddenly grew a brand new dimension of understanding out of nowhere. This new axis didn't exist in the pre-break parameter space. It is the exact, precise moment the model stops interpolating old data and structurally reorganizes itself to internalize a novel causal law.
Section 4. Measuring genuine discovery.
The real beauty of this framework is that this massive, invisible geometric phase transition leaves a very concrete footprint. It registers mathematically as a discrete, exact plus 1.0 integer step jump in an observable metric called structural G-entropy. It's an unambiguous, totally quantifiable signal that essentially screams, yes, a brand new causal rule was just generated right here. Let's look at how this actually compares to our standard toolkit. Traditionally, we monitor perplexity or loss curves to see if a model is actually learning, and those metrics degrade continuously. They slide smoothly down these nice gradual curves. But structural G-entropy is entirely different, because a new dimension either exists or it doesn't, right? So this metric doesn't slide, it jumps discretely. When you see that sudden +1 jump during evaluation, you know for sure a new causal dimension has been established. It acts as this amazing parameter-free dashboard to separate true structural discovery from simple statistical memorization.
Section 5. Filtering out hallucinations.
Of course, to ensure we aren't just measuring the model having a complete and total hallucination, the researchers propose decoupling the parameter charts and subjecting these new emergent axes to two strict mathematical filters. First up, the minimal energy path criterion. This essentially validates that the new axis is following the absolute lowest energy trajectory through the manifold. Basically, it proves the discovery has real structural stability and isn't just some weird noise-driven artifact. Second is the causal invariance filter. This ensures that the newly discovered axis remains unchanged even under different causal transformations, which confirms it's actually robust against distribution shifts. Together, these parameter-free filters theoretically, mathematically certify that the system captured a real, true law of the universe.
Section 6. Next steps for developers.
Okay, let's step back into reality for just a second. SMG is an absolutely incredible theoretical mathematical contribution right now. The paper, which is published on arXiv in the machine learning category, provides all the geometric definitions and proofs. But there is no reference code, there's no API endpoint, no Docker image, and no benchmark suite you can just go download today. It is very much a glimpse into the future of AI certification rather than a production tool you can just spin up this afternoon.
However, if you are currently working on mechanistic interpretability or AI for science, you can definitely start proxying these concepts right away. Here is some actionable advice you can use. First, start monitoring your training logs. Try to instrument a proxy for structural G-entropy so you can watch for those discrete jumps during out-of-distribution evaluation. Second, audit your parameter chart decoupling. Really review how your model's latent dimensions are entangled because, remember, true discovery requires fully independent axes. Third, just keep an eye on arXiv and GitHub. Community tooling for these kinds of theoretical papers usually drops anywhere from 6 to 18 months after publication. And finally, run causal invariance tests. You can apply existing causal inference tools to your model's latent space to sort of approximate these filters today.
Let's end on this thought. The very next time you are training a massive model and you see a catastrophic spike in your matrix calculations, you really have to ask yourself, will your model's next singularity be a failure or the birth of a brand new causal law? We're moving from an era of just guessing if AI is smart to literally mathematically certifying its intelligence. It is a massive paradigm shift, one that aims to transform AI into an engine of autonomous paradigm shifts itself. I highly encourage you to go read the full arXiv paper to see the math for yourself. Thanks so much for joining me on this explainer, and keep exploring.